go ahead and start our next unit on what we're covering, and that's waves. So the homework that's due a week from today. So homework due next Wednesday. This will be in the chapter of the book again. Chapter 8, problems 1 through 8. And we'll be covering waves. So, I guess the main thing is, what is a wave? And, so we have to kind of understand this. It's sort of related to simple harmonic motion in some way. If I'm looking at, well, first of all, what type of waves are we familiar with? Light waves, sound waves, anything else? Those are types of light waves. Yep, and radio waves, all those are light waves. And we'll see the difference. We'll go through and see the difference in a little bit, okay?
Like it goes up in Kansas, used to watch the waves with the feet.
Oh yeah, that's actually a really good example. And water waves, and all those things. One of the things about the wheat waves, that you see is like if you looked at what was going on, you just have wheat that moves back and forth in the individual stalk. But it looks like you have a wave that's moving around. And so let's go ahead and see if we can kind of look at an example of this. This is this device is a good illustrator of waves. It doesn't move too quickly or anything like that. So I can start a wave moving along here. I kind of have to put a little force on this. See, you get a nice little wave, right?
Yeah.
That's kind of what we are thinking about with waves. And what's going on? If I looked at any individual one of these things, right? I don't know the steel. I don't know what you call these. If I look at any individual one of these little barbell things, what's actually going on? This isn't moving. None of the individual barbells is actually moving in any direction, except back and forth, right?
So whatever it's moving.
But somehow or other, the wave moves in that direction, right? Well, yeah. So let's see if we can look at this again. Can everyone see this? So if you can see that any individual barbell does not move forward in any way. But somehow or other, it just moves back and forth. But somehow or other, a wave travels through here. And so why would that be the case? Well, in this particular case, and this is probably a pretty good example, you see that if I twist one barbell, the next barbell kind of has a force on it that makes it, or a torque on it that makes it want to twist. Because if I twist this one, the band is twisted. And it makes it want to twist. So the next one starts twisting, and then the next one, next one, next one. But so the wave requires something that if I move something, neighboring pieces in space want to move. And then two, there is no actual forward or backwards movement of the things that are doing the moving. All we have here is twisting. You guys can see that. It's pretty hard. I think I'm right in the way. You wanna move it over a little bit? There, is that better?
Yeah.
All right, much better. See, none of these things is moving, but by twisting it, it makes the next one want to twist, it makes the next one want to twist, and so you have this movement of propagating twistings and stuff. So that's probably your perfect, typical example of a wave. Something wants to move back and forth. Actually, we'll treat it in this case as like a simple harmonic motion. Neighboring of the same things then wants to move. And you get a wave disturbance going through it. So for instance, with like a water wave, if I have a wave going up, it wants to kind of fall down. So, and when it wants to fall down, it pushes the next one up, and so you get kind of this wave that's traveling. Sound wave. What's going on with sound waves? When I create a little pressure, that pressure exerts pressure on the neighboring air. That exerts pressure on the neighboring air, and I get this kind of pressure disturbance going through without the individual molecule moving very far. Just kind of moving back and forth. So we can do another example of a wave. It's kind of heavy. Yeah. This one, the wave, the wave here travels a little bit faster on this one, so it's a little bit harder to see, but this will illustrate another thing about waves. Oh well, this one. Does somebody want? Yeah, you can. I think so. So what we have here is a spring, right? And there's a couple. If I move it down like this, there's a spring force that actually makes the spring want to go back up. And because it's pulling down here, it pulls the next plates down, and then so that'll go down, and then that wants to be pulled up, and that pulls the next place down, etc. So if I move a little, you can see like a disturbance that goes through it, right? Actually, Alan, can you hold it in front of that kink? You'll see the wave is nicer that way. So you see that there's a wave that kind of goes through that. Yeah. So there's another thing with waves. That is, there can be multiple types of waves. I'm sure most of you have seen this. This is called a transverse wave. Because what I'm doing is I'm pulling these things down, and so if I look at any individual coil, it's going up and down, but the wave is traveling that way. So the individual coil is moving up and down, and the wave is traveling that way. The movement of the material and the wave are in opposite directions, perpendicular directions. There's another possibility, and that's called a longitudinal wave. And, oops, I didn't do that one very well. But if I make the coil a little bit shorter and then let it go, there's a wave that propagates through there. And this one, each individual coil is moving back and forth like this, and the wave is going in that direction too. So that is a longitudinal wave. The coil is moving back and forth in the same direction as the wave is traveling. What do you think a sound wave is, by the way? Yeah, it's a pressure wave. What type of wave do you think it tends to be?
Longitude.
Yeah, that's right. If I'm compressing air, I'm pressurizing it, depressurizing it, it's moving in the same direction as the actual molecules are moving. Alan, you're geoscience, right?
Maybe. Don't make it too busy.
You guys deal with all sorts of waves, don't you? And if you want to look in the earth and stuff, probably one of the main things to do is to they have those devices that shoot lead bullets in the ground, They create like little tiny earthquakes, and you can look at the waves coming up from that. There are various other devices, right, that they do to make waves in the ground.
P's and the S's, sometimes very solid, sometimes very solid.
Yeah. So one thing about waves, this transverse wave like this, if I have a liquid wave, the transverse waves don't go through the bulk of the liquid. So that's something that you can see. That's how they know that the Earth has liquid in the core, near the core. Is that they look at when they have earthquakes, they can see various places where they can't see S waves. They can tell where how big the liquid part of the core is. Anyway, so this is kind of an introduction to waves, right? So let's see if we can put some mathematical teeth in this. We're not going to do too much of this. Yeah, you have love waves and Raleigh waves, right? Now, which ones are the love waves? Okay. Wait, which one's up and down? That's the Raleigh wave, and the love waves are solid.
I hate pop quizzes.
All right. So we'll go through this. So the way that this, I'm going to kind of model this spring as like having little masses, with a little spring between these masses. And I'm not going to worry about what these masses are. They just are little masses. So for instance, this coil has a little mass, right? And each one of these coils has a little bit of a mass. When this mass is moving, it exerts a force on the next coil up. So you have to, that's going to be what's going to make the wave moving. So say that I look at this particular coil, and say I have a wave that's going up and down and traveling in this direction. What type of wave is that, by the way? Transverse wave. Okay, good. Okay, if this is moving up and down, I could graph the position in the y direction as a function of time, right? Of that little, of this mass. And if I have a wave going through, you know what I would see is I'd see something like this, kind of going up, you know, it'd go up and then come back down. And it'd probably go past its equilibrium point, come back to its equilibrium point. And if I kept on exciting it, I would actually get kind of a movement like this. So here I am, I'm looking at a single mass, or a little single place in space where this wave is going through, and if I plotted this as a function of time, I would see a wave like this. I'm doing more than a single pole, so I'm just kind of doing it constantly, exciting it up. The time it takes to go from one peak to another, or from one zero to another, or from any two corresponding parts of the wave. This is called the period of the wave. If I were to kind of draw the displacement of these masses as along here, so I'm going to kind of look at y as a function of position of x. I have y going up here and x going over here, and I plotted the position of maybe this spring and the masses at any point. I would see if I had a wave going through here, it's going to do something like this, right? So the distance between where the wave has one peak and the wave has a second peak, this is the distance now. This is called the wavelength. And that's symbolized with the Greek letter lambda. Okay. So this is, if I took a snapshot in time as a wave passed through here, you know, maybe this mass would be down, this mass would be up, or this mass would be up, this mass would be down, next mass would be up, next mass down. So if I took a snapshot in time, I'm not overlaying this very well here. You know, the wave, whatever the wave is on this spring and mass system would kind of maybe look like that. And the distance between where this is at a peak here and then this is at a peak, that's the wavelength. Okay, well we see that, you saw that waves traveled at some speed, right? So this disturbance, in space, this moves along here. In fact, if I were to look, one wavelength passes through a point every time I get one period. So if I looked at one point in space, this would go up and down back to its original position as one wavelength passed through it. So this gives me an ability, a way to look at the speed of the wave. So the speed of the wave, v, is going to be equal to lambda divided by the period of the wave. The wavelength divided by the period of the wave. And in fact, that's often written as lambda times the frequency of the wave. Frequency. Okay. So just to kind of illustrate, say that you're listening to a FM station. Let's say that the frequency of the station, I don't know, is 89 megahertz. The speed of the wave, radio waves are light waves, right? They're a type of light wave. Is a well-known velocity, speed of light we call it, c. And does anyone know what the speed of light is? Any chance? Just from background knowledge?
186,000 miles per hour.
Miles per second, yeah.
Miles per second,
Yep.
301 meters.
Yep, so it's 300 million
300
meters per second roughly.
It's 299, I think it is, 0.7 something.
Yeah, that's right. That's right. So the speed of light is this. So my question is, what is wavelength for this wave? So see if you can go get that. you know the frequency. Do you know what? Do you know what the meaning of say blue light is?
Blue is relative.
Sort of big. That's probably as right as you can see, yeah.
Well, I don't know if it's for me. Is the unit meters or?
Well, the length, right?
Yeah. Yeah. I don't know. It's like,
You get it?
How
well,
many factors in that?
with,
What's that?
I mean,
how do you convert megahertz
how
to
big is
hertz?
it?
Oh, how big is a mega? It's a million.
10
So 10
To
to
the
the
9,
6.
to the 6.
By the way, the British sometimes are confusing. Sometimes they use, well, I don't know if they use million, but billion is like a trillion or something like that. Or, no, a billion's a million. And then they're very confusing about what they call various things. Historically, I think pretty much it's standard. Do you get it?
Yeah. I'm just taking. You guys use 0? I don't know. You time it?
Times 10.
I don't know. I don't know.
89 times 10 to the
1 times 10. Yeah.
Do you guys get it? What do you have? I got 33 points. Equals 33 points.
I got 3.37.
Yeah, I got
3.3. Yeah, me too. 3.37.
All right, let's go check this real quick. Okay, so we have C, which is the speed of light, 3 times 10 to the 8 meters per second. That's equal to the wavelength times the frequency, right? So this would be wavelength times 88 times, or 89, times 10 to the 6th hertz. So I'm gonna just take that 3 times 10 to the 8 meters per second divided by 89 times 10 to the 6th hertz, which is 1 over seconds, is equal to lambda and what do I get?
3.37.
3.37 meters. Okay?
How does this?
So the hertz has a unit of 1 over seconds.
So this is
Right.
But for some reason, frequencies are always written as hertz, which has the units of 1 over second. Angular frequency is written as per second,
Per second.
even though it's radians per second. Radians dimensionless, because it's a ratio of 2 lengths.
Because it's just negative.
Yeah,
Right.
and but then but you do write omega, which is 2 pi f. You write that in units of seconds to the minus 1.
Yeah.
I don't know why the notation is what it is. It's historical. Okay, so let's talk just a little bit more about light. You know, since it's probably the most common way that we see all the time, and we know what the speed of it is. Anyone know off the top of your head roughly what visible light is?
well, yeah.
400, what was it?
400 to 700.
400 to 700, what?
Man,
Nanometers, okay,
Yeah.
we'll go with that. So, let's say that I'm interested in, like, let's say I'm interested in blue light. It's maybe 450 nanometers, say. Say lambda is 450 nanometers. What's the frequency of that light?
Nanometers today.
10 to the minus or plus?
Yeah, -9.
That's right.
yeah.
So it's good that we're getting practice with those. Get it?
6.67 times 10 to the negative 14.
All right. So let's go ahead and check that really quickly. So C is lambda times F. So if I want to figure out what F is, C over lambda is equal to F. So I take 3 times 10 to the 8 meters per second, divide by 450 nanometers, which is 450 times 10 to the minus 9 meters, or 4.5 times 10 to the minus 7. And when you plug that in, you get about 6.6,
6, 7.
yes, 6.7 times 10 to the 14 hertz. So visible light is usually on the order of about 10 to the 15 hertz, just so you know. All right, here's one for you. One more thing with light. Well, I don't know, we'll do 2 more. We're kind of getting physics understanding anyways with this, even if it's not directly useful for this. So if I look at a transmission antenna, like a long vertical antenna. Some of these antennas are actually transmitting, some of these antennas are just towers and you have little transmitters at the top. Let's talk about an antenna that is actually transmitting. There's one in town, kind of outside of town, on Old 40, that's an AM transmitter. The height of the transmitter, so this is an antenna that's transmitting the wave, kind of indicating the peaks in the waves by these lines. It's usually about lambda over 2. Maybe it's the wavelength over 4 for some, but we'll do wavelength over 2. Height is equal to wavelengths over 2. So, let's say I have an AM station. Transmitting at 1,000 kilohertz or 1 megahertz. How tall would I want to make that antenna? How tall, roughly, is the antenna? light it is. Yeah, every light wave has the same speed. It's pretty cool. That's why it's so easy to do examples with light waves, because you know the
It's always
speed.
the same.
Yeah. You get it?
Yeah, I noticed a little bit. So yeah,
What do you get?
I gotta plug it in. I have it written out.
Okay. You guys get it? 150 meters.
What, 115?
So let's go ahead and check this. So we have lambda times F equal to 3 times 10 to the 8. Seems to always be the starting point with these. I'm doing 1 megahertz. So I'd have, and I'm interested in lambda. So lambda is 3 times 8 meters per second. That's 10. Divided by 1 megahertz, which is what's a mega?
1 times 10 to the 6.
Times 10 to the 6 hertz. So I get 3 times 10 to the 2 meters, right? So H, we've got lambda over 2, would be 150 meters. About 450 feet. So big, one of those AM towers that you see once in a while, maybe about 450 feet tall is what you'd expect. Sometimes they do lambda over 4 too. That also is the work, and then you'd only have a 75 meter tower. So that's kind of, you can kind of judge on AM antennas what the wavelength of it is actually. By the way, your cell phone, it's transmitting, right? It has a little transmitter in it. Do you know what frequency it works at? I think it's 2.4 gigahertz or 2.2. I don't remember which one. What's a gigahertz? Yeah. So for a cell phone, they deal in the microwave regime, and the frequency at about 2.2 gigahertz. Is it 4.2? I think it's 2.2. I'm second guessing myself now. And what's it? So this is 2.2 times 10 to the 9 hertz. So lambda times F, still C. So the wavelength of such a signal will be 8 meters per second divided by 2.2 times 10 to the 9 hertz. And that would be, what would that be?
Yeah,
0.14
1.4 meters.
So it'd be 14 centimeters. One more. This is more physics stuff, okay? We'll do one more. Okay. Nuclear physics. We all know how an atom's made, right? Well, we don't know how it's made, but you can kind of, we know the structure.
it's made up of.
What it's made up of. You have an atomic nucleus. And And then you have electron shells or whatever around it, right? Electrons. Positively charged, these are all negatively charged. It's kind of a heart, isn't it? Anyway. Well, the size of an atom roughly, where the electrons are across, it's on the order of what we call an angstrom. Symbolized like that. Have you seen that symbol before? Chemists maybe know. You've never seen it? Maybe that's a pure physics thing. Anyway, this is 10 to the minus 10 meters. Okay? So atoms are about 10 to the minus 10, or a tenth of a billionth of a meter across. These atomic nucleuses are 10 to the minus 15 meters across. By the way, electrons are about 1/1800th of the mass of a proton. So if I'm looking at an atom, even a hydrogen atom, the nucleus has 1,800 times minimum, and closer to about 30 twice that, because there's protons and neutrons, about equal numbers. Closer to about 3,600 times more mass in the nucleus than there are in the electrons around it. And yet the nucleus has a radius of 100,000, 1/100,000 of the size across as the whole atom. So if you think of atoms, it's very interesting. I mean, if you can kind of picture that, all the mass is in the little thing in the center. Okay? This is 1/100,000 of the size of the whole atom. Now, X-rays, visible light that we see and stuff often comes from emission of light from these electrons moving around. The gamma rays and the X-rays that we often see from radioactive elements and stuff come from emission of light from the nucleus. Okay, so we can estimate a rough estimate of where you would expect to see the wavelength of these X-rays and gamma rays. So just take the distance across of this nucleus. And imagine that you have X-rays and whatever trapped inside of there. And so the wavelength, lambda, is on the order of 10 to the minus 15 meters. Just put it equal to. So, let's see if we can figure out the frequency of this light, okay? So frequency times wavelength. See, we're going to try and figure out the frequency of the X-rays that are coming out of atoms, out of the nucleuses of nuclei of atoms. So this frequency would be C over lambda, which would be 3 times 10 to the 8th meters per second divided by 10 to the minus 15 hertz. So that would be 3 times 10 to the 24, right? Oh, meters, yeah. Very good.
Times 10 to the 23rd.
Oh, yeah. 23rd hertz. So this would be the frequency of gamma rays and stuff that from nuclear decay would be about that amount. Okay, rough. Now you know all the rough estimates and all of this. Let's go ahead and we'll come up with one more formula for a wave. Hopefully there's actually quite a bit of physics that we covered today without really doing anything too tough. All right. So we saw that waves oscillate in space, and they have a wave with a wavelength of lambda. And we see that a point that on a wave goes up and down in time with a period of t. So we want to kind of combine all of these things into one mathematical expression for the wave. Okay? So I'm going to draw, this is in space, this is in time, you know, my wave, the point on the wave goes up and down with a period t. We'll call this the height that the wave, that whatever is making the wave goes up to. We'll call this the amplitude of the wave, A. Now it also oscillates in space, so as a function of position along the travel of the wave. Has the same amplitude, of course, because the wave, you know, moves things up and down the same amount. But it oscillates in position with a wavelength lambda. So, to combine these two ideas together into one single expression, what we'll do is we'll just say the wave is described, and this is not for all waves, this is for a nice wave like this that evenly oscillates. Those are called harmonic waves. The expression for the wave would be the amplitude. I'm going to just write a cosine here. Sometimes you'll see sine, it doesn't, that just depends on where I'm starting. Cosine of, and if it goes, we're going to deal with radians here. And so if I go through one full oscillation, how many radians did I go through? 2 pi, right? So if I travel one wavelength, I should go 2 pi radians in here, right? So I'm going to write this as 2 pi x over wavelength, and then if x is one wavelength, the distance traveled, then I would have gone 2 pi radians. And inside this same cosine, I can either do a plus or a minus here, and I'll tell you that that means that determines the direction of travel, either positive or negative x direction. If I go one period in time, how many radians should I have gone by? 2 pi as well. So I can combine these expressions like this. So in this case, if I move in position by one wavelength, change this by 2 pi radians. If I move in time by one period, change this by 2 pi radians. This minus sign, I'll indicate what that means in just a second. So this is my mathematical expression indicating how high up any little point on the material that carries the wave is. Okay, so I'm going to put this as y. You'll see that. I can clean up a little bit inside of here. So amplitude, cosine, I can factor out a 2 pi for both of these terms, right? Right, this is 2 pi times x over the wavelength minus t over the period. It is actually customary to factor out a 1 over wavelength as well. So I could write this as a cosine of 2 pi over wavelength x minus, and then lambda over period time. So if I multiplied through these parentheses by 1 over wavelength, I'd get x over wavelength times minus t over period. See how that works? This lambda over period, what was that?
Speed of time.
That was the speed of the wave, right? So this was a cosine of 2 pi over lambda x minus period of speed of the wave, like that. And so this will be, and that if I wanted to just be at a peak of the wave, that would be where this x minus vt would be the same thing, right? X minus vt, if that's a constant, that would mean that this cosine would be a constant, right? So that's kind of, if I'm on the x minus vt, that'd be at a point here where I'm traveling at the top of the wave. I'm traveling along the wave if I'm moving, if this is constant. If this is constant, I'm moving with the wave. Because the cosine's not changing. And so this would mean, if this is equal to a constant, then moving with wave. So if that's a constant, then that would mean x would equal to some constant plus vt. So that means x increasing with time. This minus sign means that the wave is moving in the plus x direction. If I had a negative, if I had a plus sign here, it would be moving in the negative x direction. So wave moves. Wave moves. If I had a plus here, waves move in negative x direction. And I think I better quit today. That's the mathematical expression that we're going to be dealing with as far as waves are concerned. We'll do some practice with that. What's that? No, I'm just, well, those, one of those is the y, the other is y. So I started measuring x is 0 with Hopefully it's been consistent.
It's over 180 degrees over summer, 90 degrees
Well, so if I'm dealing with so electronics, we get all sorts of good.
I'm gonna try and grade it out.
Okay. That's why you don't hand saw it on
Train track.
on the cell phone.
Oh, yeah.
Capacitance, if you screw up on that kind of big range.
Well, no, it's inductance that really kills you in the high frequency. Is that impedance Is it raining out?